Thank you for the introduction, Reuven. I would like to start with a dilemma. Let's assume I have some competitors that I don't have his price in real time, and I want to reverse engineer it, so I'll be able to use it in the live environment. Assume I ran some XGBoost model on this specific data set, and I got 2% error on the training set and 10% error on the test set. If that doesn't say anything to you right now, it's still okay, don't worry. But given that it is it a good model or not? What about if I run another algorithm on the same problem, same data set, only this time I'll get 10% error on the training set and 11% error on the test set? Is this a good model? And the better question is, which one out of the two is the better model? Now, this is probably the most common problem that we have in supervised machine learning, the problem of model selection, which model to choose. And there are good news and bad news. I'll start with the bad ones. First, there's no textbook answer, okay? Otherwise, I'd be out of a job, hungry for bread on the streets, okay? Second is that in order to master the entire concept with all the different variants, it would take us approximately 2 days, go through some math, statistics, and unfortunately, or luckily for you guys, you have only 30 minutes with me. The good news, however, is that the intuition is super powerful and super easy to understand. And my goal in this session will be that each and every one of you, by the end of this session, will be able to answer these types of questions by his own. The name of the session is Key Concepts in Model Selection. My name is Adar Ben Aderet. I'm a team leader at Earnix. My main focus for the past 6 years or something like that has been machine learning. And to tell you the truth, I'm super excited to be here today. And the reason that I'm super excited to be here today is because this tool I'm going to talk about is so powerful. It's so powerful that it spreads across industries. I don't care if you work in banking, insurance, bioinformatics, cyber, as long as you're doing supervised machine learning, this methodology will hold. Second, it's data agnostic. It doesn't care if you're working with tabular data, image data, signal processing, or any other data applicable. Third, it will work the same if you will use a simple linear model or a complex deep learning model. Okay, so it's algorithm agnostic as well. And essentially, it doesn't care about your target, your cost function, or your optimized metric. So pretty much applicable all of the time. Just so we'll understand the outline of this session, we will start with defining the building blocks for our problem. We will then finish up with a short discussion about data partitioning. We will then have a short simulation regarding model complexity and understand how model complexity relates to the different errors across the different sets. Afterwards, we will define a concept called the generalization error. We will decompose it and see how that combined with the model complexity help us in formulating the Bias-Variance Dilemma. We will then talk about each of the components. We'll have 2 practical examples, okay, just to make sure we control the dilemma, know how to solve it. And we will have a very short use case overview, okay, of how we do things or what do we do in advanced machine learning nowadays at Earnix in the industry. So, you know, model complexity, overfitting, those are, and all of those terms are probably, hopefully by the end of this session, you will get to know them just a little bit better, or much better, I don't know. Now, there might be a lot of reasons why our machine learning algorithm might malfunction. Some of them are listed behind me, and there are probably dozens more. And what most of them have in common is that they can be formulated within the framework of the Bias-Variance Dilemma, which is quite impressive. There are 2 concepts I want to talk about, model selection and model assessment. So model selection basically means out of a set of models, how do I choose the best one? Second, model assessment is, given that I chose a specific model, how well is it going to perform on an unseen data set? After we lay down those building blocks, we're able to utilize them in the concept of data partitioning. So data partitioning is, I can talk for 2 days about that. That's a different story for a different session, maybe next summit, who knows. I'll touch base upon the most common methodology for data partitioning that we have in machine learning nowadays, which is the train, dev, test. Let's start by defining the first two sets. So we take our full data set, partitioning it into three components. The first is the training set, to which we fit our algorithm on, okay? Second is the development set or validation set, depends on how you call it. It's the same thing, basically. On that set, we perform the model selection, okay? And that is because our training data, we can't use the error there because it suffers from something we call optimism. We can actually quantify that measure, but again, different story for a different session. Basically, what we'll do, we'll take our algorithm, fit it on the training data, see how well it does on the dev set data, then gain some insights, get some ideas, which hyperparameters to play with, which variables to select, to add or to remove, then move back to the training set and refit the algorithm, and see then how well it does back on the dev set. We will iterate between the two different sets until we will select the best model. Once we have done that, we will take a look at the test set, and essentially, it's being used for model assessment, meaning the sole purpose of the test set is performance evaluations. Once I picked at the test set, once I looked at it, I can't look at it anymore. Okay, I can't use it. I can't derive insights from it. I can't improve my algorithm afterwards. And basically, our data science team, our goal is to minimize the error on the test set, because that's obviously what's going to reflect the reality, what will happen in the field. So after we set down the different building blocks, we can move on to defining model complexity. Let's go full data science and have ourselves a nice simulation. So I chose a very simple problem to define. We want to predict housing prices based on their size. Now, since in our Python environment we're practically gods, we know the generating function. We know the true state in the world, okay? And for some reason, that's it, okay? Unfortunately, that doesn't quite look like what we usually have in our core systems, right? We don't see anything behaves that nicely. So let's add up some noise and sample from that distribution. So we'll have something like that. Now, that looks like something we recall and familiar with. But we can still see the true signal. Even if we weren't aware of the generating function in the background, we'd still be able to understand what the true signal is. We're all set to go and fit our algorithm, right? So not quite yet. As we've talked about, we need to partition the data first. So in this case, I partition the data into two parts, the training data and the dev set data. I also have a test set. I put it aside. I'm not even looking at it at this stage. That's how strict we're supposed to be. Okay, there are some tests we're supposed to perform on the test set, but generally, don't pick at it at all, okay? In this case, just arbitrarily, I use 70-30% data partitioning. The training data to which we will fit our algorithm are the rate points. The points that will be used for model selection will be the blue ones, and the dev set data. So now we can start fitting different models. So let's start with a very simple model. For instance, the simple average. Basically, we fit a 0th degree polynomial, meaning a constant, to our training data. Now, by default, we minimize the MSE, which means basically it's equivalent to maximize the R square, which we will report on the left-hand side of the slide. You can see the training data in red, and you can see the prediction, okay, in blue. We see that the average is approximately $65,000. Okay, makes sense. Overall, looks like a pretty bad model, right? Like, no matter whether I'll fit this line, it will never be able to capture the signal that we even logically see that we have in the training data, right? But I learned not to make decisions based only on my training data. Let's see how well we do on the dev set. So let's score it. Once we will score it, we will see the predictions with black axis, and we see that the model fits just as poorly to the dev set. Not surprising, we see the R square is still 0. Okay, perhaps we should try a more complex algorithm, one that will capture the signal. How about a 10th degree polynomial, for instance? So once we will fit that, we will see that the R squared for the training data will skyrocket into 0.95. Seems like we found our model right. Before we make any decisions, let's take a look at the graph that we've seen before on the training data. This is what we get. Doesn't look so nice, right? Logically, it doesn't make sense. But the R square is so high, so what happened here? And one hypothesis will be that the model was so complex, it has so many degrees of freedom, that it actually was able to go through almost every single data point that we have in the training set and fit to it almost perfectly. So perfectly that it somehow captured some training data-specific noise, okay? But there is only one way to check this hypothesis. Let's see how well we do on the dev set. So once we do it, we see this graph. Of course, it fits poorly. We see a huge decrease in the R-squared metric, which means we were right to consider that this algorithm fit very well on the training data, but very poorly, okay, on other sets, because it was able to predict or to fit some training data-specific patterns. So what? So there is no best model, no good model. So the truth lies somewhere in between, and we should perhaps try to reduce complexity now, not to give it so much degrees of freedom. So how about a third-degree polynomial? Once we will fit it, we will see this graph, which looks like it fits the training data quite nicely. The R-square is relatively nice. Let's see how well we do on the dev set. Looks nice, right? The R-squared is relatively okay. We had a slight decrease of performance, but that's expected. I would say that through the process of model selection, out of the 3 models we explored, this is probably the best one. Now, okay, we've selected the best model. What now? Just for closure, let's score the test set. We're revealing it now. And we see that we get pretty much the same error we had on the dev set data, which encourages us and feel good about ourselves, and this is the model that we go to market with. To summarize this part of the simulation, I would like us to understand the main point or the key phrase from it, that there is some sort of a relationship between the model's complexity and the errors across the different sets. And not only in the sense that simple models will have high error on the training set and complex will have low, but what happens between the different sets for the specific algorithm. So let's summarize it in a table. First, we started with a simple average model, which was too simple. It didn't even fit on the training data. And the R-squared was 0 for both sets. Okay, it did poorly on the training set and just as poorly on the dev set, so not too much change. Second, we tried the 10th degree polynomial, which was obviously too complex for this problem. We saw that the R-squared for the training data was very good, but apparently it was too good because we managed to capture some training data-specific patterns that were not existing in the external data sets in the dev set data, and hence the decrease in the performance. Now that we've pretty much understood the concept of model complexity, I would like to move beyond that. Okay, I would like to define something that is called the generalization error. So basically, generalization error measures how well does an algorithm fit or predict to a new and unseen data set. But that sounds awfully familiar, right? Like this definition, we've seen that before, right? For the test set, it sounds pretty much the same. And that's because I lied to you earlier. We don't want to minimize the error on the test set. We want to minimize the generalization error. And the test set is just our proxy, okay? And if we want to decrease the error to minimize it so bad, let's decompose it. Usually the error has 3 components, 2 of them which we can control, which are the bias and the variance, and one which we cannot. We call it the irreducible error for regression tasks, Bayes error for classifiers. Now, let's combine this concept of generalization error and model complexity together. The next graph is an important graph. I will give you 20 seconds to explore it, then we will talk about it. And then I'll give you another 10 seconds to explore it before we will move forward. Okay? So take 20 seconds, and we'll continue. Looks interesting, right? I hope some of you got it. And if not, there are 2 things I want you to pay attention to. The first, how the generalization error behaves with respect to model complexity. We see that for simple models, it's relatively high. It decreases until some optimal point, okay, some minima, and then shoots back up for complex model. The second is how the different components of the generalization error change with respect to complexity. We see that the bias and the variance behave differently, okay? For models, some models will have high bias and low variance, and vice versa. So we have some sort of this behavior, and that basically is the whole essence of the trade-off. Still not clear? Let's connect it to what we've seen before in the simulation. So, by the way, this is given truth. We're not going to prove that right now. If you want to deep dive into that and see the rest of the simulation that we have, contact me later. I'll be more than happy to show it to you. But just to connect it to the simulation that we've seen before, if we change the x-axis from complexity to what we actually had, so the polynomial degree, and we'll place the three different models on that graph. We'll start with a simple average model. It's simple, so it will be on the left-hand side. So apparently that model had high generalization error. Yeah, we saw the R-square on the dev set was 0, so very low. And apparently it suffered from something that is called high bias. On the other hand, the very much complex model that we had, the 10th degree polynomial, was too complex, fits all the way on the right-hand side, and also had quite a high generalization error. We had R-square of 0.77 on the dev set. And apparently it suffered from something that is called high variance. The just right model that we had was somewhere in between, and it was able to balance the variance and the bias. Okay, and if we'd like to just, in case it's not clear just yet, let's formulate the dilemma together. The dilemma comes to answer the question of which model should I pick with respect to its complexity in order to balance between the bias and the variance so it will minimize the generalization error. So I'll give you 10 more seconds and then we will move on. Okay, so you know what, I'll move back. Before we move forward, I guess you're all like, great, looks very interesting. However, in the end of the day, I'm fitting a model. How do I know if it's high bias, high variance, complex, not complex? I don't know what to do with this thing. So in order to mitigate or deal with this dilemma, I'll show you my own personal favorite tool to do it. There are many others, the error decomposition schema. So basically what we do is we list the errors from top to bottom. We'll have the irreducible error, training set, dev set, and test set errors, and we'll calculate the difference between each of the sets, okay? We'll deep dive into each one of the components in just a second, but the difference between the training set and the irreducible error will be the avoidable bias. The difference between the test or the dev set to the training set error will be called the variance. Now, let's talk about the different components. Let's start from the irreducible error. So basically, the irreducible error is the error that the best regressor or classifiers can achieve at a specific task. And what do I mean by that? So since we're in the field of AI, let's have an example from image classification. So basically, a dog classifier. Usually people show cats. I'll show dogs. I like dogs. So how can we approximate a concept such as the best model or the lowest possible error for these sorts of things? So I would say maybe we should take a veterinarian or a dog expert, if such a thing exists, and let him classify it for us. You know what? Let's even take the average human. So is that a dog or not? It's a dog, right? What about this one? Or maybe it's a wolf's cub, I don't know, but still, I think it's a dog, right? What about those two? A bit trickier, but I'm sure that an expert in the field would say, yeah, the left one is a Siberian Husky, the right one is the gray wolf. But what if I add up some noise? Not so clear now, right? If I change the angle a little bit and take a photo from the back with a blur, can anybody, even a dog expert, really know? A vet really know? Will he be able to classify it? I think not. So there are actually two things we need to take from this. First, the irreducible error always exists. If it's due to noise or sampling error, but it exists, it's always there, even if we can't quantify it. In some problems, it's very easy to quantify it, as we have done here, as we can do here, actually. While in others, it's hard or even impossible. Usually in our field, it's very, very hard or impossible. So just a little joke. Actually, there was some classifier who got that wrong. Yeah. OK, let's move on. So let's move on to the next ingredient. I promised you intuition, so I'm not going to deep dive into formal definitions. But essentially, the bias is the difference between our model's average prediction and the true value. Doesn't tell me anything. OK, I'm not a statistician. I don't know. But in the model selection context, we measure it by taking the difference between the training set error and the irreducible error. If we would like to think of a high bias model, okay, where that gap is big, we'll think of the simple average model that we've seen earlier. And what did we see there? We see that the model was too simple, that it wasn't able to fit the true signal, even for the training data. That's why the gap is so big, okay? And that happens because our model failed to understand the relationship between the features and the target. This phenomenon is called underfitting, because basically we underfit even on the training data. An example would be a simple average model, or basically for some tasks, some linear model. Let's move on to the next component, the variance. So the variance is a measure for spread or variability and dispersion. In the context of model selection, however, we're talking about the difference between the dev set error and the training set error. And basically, it reflects how well does our model generalize to new and unseen data sets. And a high variance model would be, for instance, the 10th degree polynomial that we've seen earlier, or deep learning model, complex deep learning model. And if we have this problem of high variance, it means this gap is big, okay, between the training set and dev sets. Because our algorithm was so complex, the training set is very, very low, so we do very well on it. But during that process, we were able to capture some training data specific patterns that does not exist in the rest of the data sets. And hence, for other data sets, such as the dev set, we will have high error, and hence a high variance. So just to finalize the bias-variance dilemma model complexity generalization error part, before we move on to the practical examples, I want you to explore this graph. Okay, the money shot is in the middle. Okay, we'll have two models, simple one, complex one. We would like to plot both training errors and dev set errors. So the simple one is the one on the left. Obviously, it goes to the left part of the x-axis. The complex one will be on the right. Obviously, it will go to the right-hand side of the graph. And let's start plotting the training error. So for the simple average model, think of the simple model. Okay, simple average, think of it this way. What do we expect the training error to be, high or low? You know that, obviously, if it's too simple, we will have a high training error. So it will be somewhere here. However, for the complex model, we can actually see it fits very well to the training data, right? It goes through all of the points, basically. So we will have a very low error for the training set. If we connect the two dots, we will usually see something like this. If we do the same exercise for the dev set, let's start with the simple model. So the simple model, you know, I'll ask the question, how do I expect for the average to change between the training set and the dev set? Probably not by much, right? So the dev set error for the simple model will be approximately the same. However, for the complex model, we know it's a whole different story, right? What happens there? We know that while we fit very good to the training set, we do poorly on external data sets such as the dev set, and will be somewhere here. If we connect the two dots, usually we see the familiar U-shape that you're already familiar with. And in general, when we come to classify our specific model, we will say that simple models will usually be on the left-hand side, and they will suffer from high bias. It will be shown with high training error, and dev set error that is pretty much the same. And the complex models will be characterized as usually a high variance problem, where we'll have a very good error on the training set, but we'll generalize poorly to external ones such as the dev sets. Of course, as I said before, the truth lies somewhere in between when we mitigate the two. Now, let's move on to the practical examples after we covered a lot of theory. So, but before that, that's probably the best way to explain overfitting. So you can take everything I've said before for the past 25 minutes and just look at that for a second. Now, let's move on to the practical examples themselves. We'll use the same tool we were familiar with 5 minutes ago, the decomposition schema. And let's move on to the first example. So let's assume I have some regression task where I have an irreducible error of 5%. And I ran it across the different sets, and those are the relevant error metrics. So we have 6, 11, 12. Okay, what's the diagnosis? What do I have here? So let's pull up the schema and plug in the errors on the left-hand side, calculate the differences between the different sets on the right-hand side, and let's analyze what we see here. So we see that out of the 12% overall error, Only 7 of them we can play with, okay, are reducible. And out of those, in this case, it's even not just 5, it's 6% variance related. So in this case, we have a high variance problem, an overfitting problem. And we can see it by seeing a very low training error set and a very large dev set error. How do we mitigate this problem, okay, of overfitting? So the rule of thumb is reduce complexity, of course, but another solution would be acquire more data. However, that's usually not a practical tip. So more practical ones are reduce the number of features, increase the regularization parameter or the dropout percentage, try a simpler algorithm, or for sequential algorithms, decrease the number of iterations, so epochs, number of trees, and for tree-based algorithms, just decrease the depth. Of course, there are many other solutions. We're not going to touch upon those. Second example, same regression task, 5% irreducible error. Only this time we get the following metrics for the algorithm that we ran. What do we have here? What's the diagnosis? Again, let's pull up the schema. Plug in the errors on the left-hand side, calculate the differences on the right-hand side, and let's analyze it. So we see that out of the 12% error that we have, again, only 7 are reducible. And out of those 7, we see that 6 of those are actually bias related. What does it mean? It means we can see that our training error is relatively high, so high. Why is that? Because we didn't capture the true signal even on the training set. But we do see that it generalizes relatively well, okay, from the dev set to the test set, pretty much the same error, right? 11, 12, 12. How do we deal with that? So the rule of thumb for underfitting is increase complexity, of course, as we've done in the simulation. How do we do it? So we can increase the number of features, add polynomial or interactions, decrease the regularization parameter, try more complex algorithm. And in case of sequential methods, just increase the iterations. For tree-based algorithms, increase the depth. Okay, the last part, thank you. The last part I would like to talk about is what do we currently do with all of this in pricing today. Okay, it's going to be a very short slide, but the concepts are very important. So I bet half of you are like, okay, very nice. However, you know, I just run GLMs in Earnix, I don't know. But everything we've seen up until now is applicable for GLMs as well. Okay, that is the first thing. But if you're talking about more advanced machine learning usage, I can list 3 cases. Actually, here it says 2, but there are actually 3. So first is for your auxiliary models. So everything pretty much but the demand models, where you care about predictive power. So you'll try to fit some, as we've seen before in other sessions. We'll try more complex algorithms. So for there, of course, this method applies. And the second use case that we have is within the demand model, what I like to call as super features. Basically, it's complex machine learning algorithms that we plug into our demand models. Think of an example, a good example would be market components. We don't have them in real time, but we want to use them. We have them for past data. So those are very sophisticated machine learning models that we plug in the demand model. And obviously, for those models, we can use everything we have just went through. And the last thing is the hybrid modeling technique, which basically relies on GBM. And in order to build a good hybrid model, you need to know the concepts of error decomposition and to know this dilemma. So just to summarize everything we went through up until now, or to summarize the entire session. We've started by laying down the building blocks for the problem. We've talked about data partitioning, about the 3 sets, understood which one is applied to which problem. And then we moved on and had a quick simulation to understand the relationship between model complexity and the different errors on the different sets. After we did that, we looked beyond model complexity, and we've defined a concept called the generalization error. We realized that's what we wanted to minimize. We combined that with the model complexity part and phrased or formulated the Bias-Variance Dilemma, okay? How do I choose the best model in order to balance between, with respect to its complexity, to balance between the bias and the variance, and by doing that, to minimize the generalization error. After we did that, we decomposed the error, talked about the different ingredients, and we've seen 2 practical examples. We learned how to debug those problems of high bias and high variance, and had a quick overview of use cases that we have currently in the industry. One last thing, and that's probably the most important one, don't accept pills from strangers. Thank you very much, everybody.